Okay, so Lewis structures. This is a term for what we've been doing. This is where you show lines to represent bonds, and then you show double dots or a colon to show paired electrons that are not involved, usually in bonding. Okay, so it's named after Gilbert Lewis. He was a great chemist with electrons. Check out his Wikipedia page when you have some free time. It's excellent. Click the link below, right? Is that a thing?
Yeah.
Okay, so this drawing method represents the valence electrons in bonds. Unshared pairs look like this. They're not involved in bonding. Put in, asterisk, because nothing is ever completely true in chemistry. There are exceptions that we'll even go over this year. But anyway, the central atom is generally the least electronegative for these drawings. So whenever you're looking for all right, what's going to be the central atom, you can look for the least electronegative. That's not the best way to do it. There's also the most single bonds that you could kind of attach. That's usually good. Like if you see a carbon, no matter what everything else is, carbon's probably going to be the central atom because you can connect you can make 4 bonds with it, up to 4 bonds. Okay, so let's talk examples. If we have hydrogen, how many valence electrons does hydrogen have? 1, yeah, exactly. And then the other one has another one, and then you connect them, right? So the Lewis structure for this would just be this cleaned up, all right? And by cleaned up, I mean check the angles if you can, check the AXE, make sure everything's correct, and then draw it again with the dots and dashes, as you would say, all right? The dash being the bond, and then any dots would be the unpaired electrons. Now, this example doesn't have any, so this would be the final Lewis structure for hydrogen gas. Fluorine, although, has 7 valence electrons. So for the Lewis structure, you'd have to draw them all, and you have to keep them there. All right, and then you notice there's 2 unpaired. They form your bond, all right, so you can link it together. And you'd look at the AXE and all that stuff. Well, this is just linear, so there's nothing really to do. So the cleaned up or the final version would just be F-F with the electrons around it, just like so. So you'd have 6 electrons around it, and then the bond, that gives you 8, and then the same thing on the other side. Okay? And then, like I said, that's what we've been doing in here. Okay, this you're gonna like more. The structural formula, it's the same thing, but you can ignore all the unpaired electrons or unshared electrons in there. So for fluorine, like we just had it, with all of the dots around it, the nice thing about the structural formula for this is it would just be F bonded to F, and that's it. Now, the thing that stinks about the structural formula is it's harder to tell if you bonded everything correctly because you can't count to 8 now. Like with this one, you can see, all right, 2, 4, 6, 8. Okay, everything's cool. And then 2, 4, 6, and 8. Okay, that's good. With this one, you only see the bond there, so you can't really check your work to make sure that it's correct. All right, with hydrochloric acid, H is this, Cl is this, and then you bond them together, all right? And the structural formula would just be HCl. Again, you can't tell if it's correct or not from that, all right? But it makes drawing it a lot easier, all right? Any questions with that? No? All right, that's structural formula. All right. Bonds, all right, single bonds, 1 pair of electron shared between 2 atoms. A double bond is 2 pairs of electrons shared between 2 atoms. And then a triple bond is 3 pairs of electrons shared between 2 atoms. All right. So we've seen this with hydrogen bonding to itself. We could see a double bond if we wanted to see maybe a carbon. And let's say the only thing we can connect to this is oxygen. All right, so a couple oxygens. All right. So I'll put 1 oxygen over here, and maybe I'll draw its valence electrons around it. All right, so there's 2 singles. All right, well, how are they going to connect to the carbon? Well, yeah, potentially double bond, since that's kind of where I'm alluding that we're going. But let's just connect one for right now. And let's say there's another oxygen we need to connect to this as well. So I'm going to draw another one. All right, we're going to connect them. And now you can see there's two more dots on each of these. So we can connect these up here and make that double bond. All right. And that would give us our double bond. Now the question for this would be like, well, what shape would it be? Would it be linear? Would it be bent? How would you figure that out? What's the AXE for it? So what's the AXE for this? AX2. What do you know about AX2? Yeah, triatomic, linear, and the angle? 180. So when you draw your final version of this, you're going to draw it as a straight line. All right, you're going to draw it as a linear molecule. So taking this and cleaning it up, we would go, all right, carbon, there's our oxygen, there's our double bond, all right, just as we saw before, all right. What else do we need to add to this if it's the Lewis structure? Yeah, the electrons, exactly. Now, the electrons, you can't just throw them on here. You actually have to think about where they would go. And think about it like this. If you had 3 electrons that you were going to put on just any atom, like boron, right? You know how you make it a triangle? You do the same thing for this. You would make the pairs of electrons kind of be off to that angle as well. So if you kind of were to put a dot in the center of the oxygen and draw lines out from it, you would get that 120 degrees. So it would look something like, all right, here's one for those electrons, here and here. So they're going to be at 120 degrees. So we'll give it that kind of shape there. Is it a big deal? No, it's not a huge deal, but that's the way it should be. All right, same thing for this side. And have them like there. Okay, and that would be the Lewis structure of it. What would the structural formula look like for it? This is Lewis. All right, and then structural would be what? Yeah, without the electrons. So structural formula would look something like that. All right. Okay, do you know anything that's triple bonded? Yeah, Jacob? N2, good. All right, N2. So here's one N. All right, we have 5 valence electrons, right? We have 3 unpaired electrons. So if we put another nitrogen, all right, where would we put the double bond? Top, bottom, left, right? Yeah, I'd put it on the bottom so it's far away. And then single, 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 and then they just get connected. So this one gets connected here, here, and then there. So you get a triple bond between them. And it would look like this when you clean it up. That's the Lewis structure, and then the structural formula would just be without the dots. Okay? All right, cool. All right, why don't you guys try this one and this one since we already did this real quick. All right, so whenever you're figuring something out, the first thing you should do is figure out what the central atom is. So out of carbon and hydrogen, what do you think it's gonna be? Yeah, because it can bond the most amount of times. All right, so I'll draw a carbon. There's 2 carbons. I'm going to draw them next to each other because it's really, really likely that they're going to be bonded together because the only other option is hydrogen, and we know hydrogen can only bond to one thing, right? So step 1 would be doing this. Step 2 is nature likes to balance things out, okay? You have 4 hydrogens, so if you have 4 hydrogens, 2 carbons, split them up. All right, so each carbon's going to get 2 of those hydrogens. All right, so I'll put one here, here, and then here, and here. Again, nature likes to balance things out, okay? Okay, now we're out of atoms, right? We have our 2 carbons, 4 hydrogens. What do we do with these little dots right here? Yeah, we form a double bond. So we'll join it together. And this is a great rough draft, all right? Now, let's take a look at it. To figure out what the final draft is gonna be for this, we have to figure out the AXE for everything. All right, so it's gonna be AX something. So let's look at this carbon first, all right? This carbon, the left carbon, is connected to these three things, right? Okay, so it's AX3. Are there any unpaired electrons around this carbon? No, right? So it's just AX3. So what do you know about AX3? Yep, trigonal what? All right, trigonal planar. Good. The angle? 120. All right. So we have trigonal planar, 120, AXE. All right. The other interesting thing about this is because it's trigonal planar, it's also going to be sp2 hybridized, which is what we just went over with hybridization. And where do we get that from? It has the same shape, or it's going to have the same shape as anything in boron's group. All right, anything in group 13. It's going to have that in there. Now, if we drew out all the electrons, you would actually see the sp hybridization. We're not going to do that because that's going to be a little bit above what we're doing this year. But if you see trigonal planar, think sp2. All right. What about the other carbon? What's that going to be? AX what? Yeah, it's going to be the exact same thing, right? So you don't have to rewrite anything. You just draw another arrow to that one and say, all right, that one's going to be the same thing. AX3, sp2, trigonal planar, 120 degrees, all of that. Okay, now, did we draw it properly? Is that a good final draft? No, you can make it look better, right? What would you do to make it look better? What's that? Get rid of the dots, good. What else would you do? Well, it's a double bond, right? Double bond. Yeah, we'd clean that up, right? Make it look nicer. Would you do anything, Brian? Anything? Yes, very good. You'd angle the hydrogens, right? So it looks like AX3, right? How would we do that? I'm glad you asked. Look how nice this molecule is. All right, so something like that would be great. All right, it's AX3. It's trigonal planar. You can see it's trigonal planar, right? And if you built it, it should look trigonal planar. So it has a carbon in the middle, another carbon, and then the two hydrogens, and then the same thing on the other carbon. All right, and if you turn it, you see that it is planar, right? It's all on the same plane. All right, good. So that's our first example. Now, is this the Lewis structure or is this the structural formula? Good, it's both. Yeah, it's both, right? Because there's no extra electrons we would need to put on here for the Lewis structure, right? So it is both the Lewis and the structural formula. Great. All right, let's go to this one. What do you think the central atom's going to be? Yeah, carbon, right? Because it's the same idea. We have a carbon. Usually if you see carbon, it's going to be a central atom. And again, how do you know that? It has the most unpaired electrons, all right, when you're comparing it with that and hydrogen. I'll always bond them together first, all right? And there's two hydrogens. So we want to even this out. We'll put one hydrogen on each carbon. So I'll put one over here. I'll put one over here. And then you end up with this. What do you do next? Triple bond, right? Okay. And let's look at the AXE for this one and see what its shape should be. So this carbon right here is bonded to a hydrogen and then bonded to a carbon. So what's that? AX2, good, which is triatomic what? Good, triatomic linear, the angle. Good, 180, all right. And the new thing with this is the hybridization. So the hybridization for this one is whenever you see this, it's gonna also be sp. So triatomic linear, 180, sp, all right? So sp was linear, sp2 was trigonal planar. What was sp3? Anybody remember? It was tetrahedral, all right? Okay, What about the other carbon? Same thing, right? You can see that this carbon's connected to another carbon and a hydrogen, so they'll both be this here. Does that look linear? Yeah, it looks good. So all we have to do is clean it up, right? So let's clean it up. And we'll have carbon triple bonded to a carbon, single bonded to a hydrogen. Okay, now, Lewis or structural? Also both, right? Polar or unpolar? Why? Okay, yeah, the pole on each side is going to be equal. Also, it's a hydrocarbon, right? And there's a shortcut for figuring out polarity for those. They're always non-polar, okay? But yeah, you could fill in the numbers, and you can see that it's going, for example, 2.5, 2.1. It's going in this direction, and then this one is the opposite. Going in this direction, opposites cancel out. All right, so it's just going to be the same thing. This is going to be the same thing. It's going to cancel out as well. All right, so it'll be non-polar as well. Any questions with that? Nope.